At the heart of every smartphone, tablet, and laptop is the Central Processing Unit, or CPU. It's the engine that drives all the computations and processes we rely on daily. Without it, our devices would be nothing more than sleek, inert shells. The brain of your device. It's a complex piece of engineering, a marvel of miniaturization, packed with billions of transistors working in harmony. The CPU performs calculations, makes decisions based on those calculations, and orchestrates every action, managing the flow of information and resources within your device. It's the conductor of a digital orchestra. From opening apps to streaming videos, handling background tasks, and even managing your device's security. But not all CPUs are created equal. They come in different shapes, sizes, and with varying capabilities. Laptops demand raw power and sustained performance for heavy tasks like video editing, gaming, and software development, while smartphones need to be incredibly efficient to save battery, allowing them to last throughout the day on a single charge. This power versus efficiency trade-off, this delicate balancing act, is the core challenge of CPU design, pushing engineers to innovate and find new ways to optimize performance and power consumption. Companies like Intel traditionally focus on high-performance CPUs, prioritizing speed and processing power for desktops and laptops, where power consumption is less of a constraint. While Apple and Samsung, among others, prioritize efficiency and low power consumption for mobile devices, where battery life is paramount. The earliest design decisions, long before manufacturing even begins, fundamentally determine whether a CPU will be a speed demon, capable of handling the most demanding tasks, or a battery saver, optimized for longevity. Every device's character, its strengths and weaknesses is ultimately defined by these initial choices in CPU design, shaping how we experience technology daily, influencing everything from how quickly our apps load to how long our batteries last. The journey of a CPU starts not in a sterile automated factory, but in the collaborative minds of engineers, architects, and designers, balancing performance, striving for the fastest possible speeds and responsiveness, power, minimizing energy consumption and heat generation, and purpose, tailoring the design to the specific needs of the target device. That's why CPU design is one of the most important, and arguably one of the most challenging and fascinating fields in tech, constantly pushing the boundaries of what's possible and shaping the future of computing. Designing a CPU is a multi-stage process, a complex undertaking that requires expertise from various engineering disciplines. It's not just about assembling components, it's about orchestrating a symphony of electrons to perform calculations at incredible speeds. Each step is as complex as the last, demanding meticulous attention to detail and a deep understanding of physics and computer science. The process involves countless hours of simulation, testing, and refinement. It starts with architecture design, the foundational blueprint upon which the entire CPU is built. This involves choosing the instruction set, determining the number of cores, and deciding on the cache hierarchy. These choices have profound implications for performance and power consumption. It's about setting the CPU's fundamental capabilities, defining its strengths and limitations before a single transistor is even considered. This stage requires careful consideration of the target applications and workloads. Next is logic design, the stage where abstract ideas become concrete circuits. Here, engineers use hardware description languages, or HDLs, to map out precisely how the CPU will actually function, defining the behavior of every component and connection. It's like writing a detailed instruction manual for the chip itself. Then comes physical design, a critical step that bridges the gap between the logical and the physical. This involves arranging billions of transistors and microscopic wires, connecting them in a way that ensures optimal speed and efficiency. It's a complex puzzle where every piece must fit perfectly. Every detail matters. The placement of each transistor, the width of each wire, because tiny changes can mean big differences in performance or power use. Even the slightest imperfection can compromise the entire design. The final step is verification and validation, a rigorous process of testing and debugging. This is where engineers run exhaustive simulations, subjecting the CPU design to a barrage of tests to catch any flaws before manufacturing. It's about ensuring that the CPU meets its specifications and performs reliably under various conditions. A single bug at this stage is relatively easy to fix. It's a matter of tweaking the design and rerunning the simulations. But after production, a bug becomes a disaster, potentially requiring a costly recall and redesign. Only after passing these rigorous checks After demonstrating its ability to perform flawlessly, does a CPU design move forward to manufacturing? It's a testament to the dedication and skill of the engineering team. Each stage is a blend of creativity, science, and precision, a delicate balance between innovation and practicality. This intricate dance, this complex interplay of ideas and processes, is what ultimately brings the digital brain to life, powering the devices that shape our modern world. With the design finalized, it's time to turn sand into silicon brains. Ultra-pure silicon is melted and formed into a flawless crystal ingot using the Czochralski method. This ingot is sliced into thin, mirror-smooth wafers, each one the foundation for hundreds of CPUs. The wafers are polished to perfection, as even a speck of dust can ruin a chip. All of this happens in ultra-clean factories called fabs, where workers wear special suits to prevent contamination. Companies like TSMC and Samsung lead the world in producing these silicon canvases. The purity and precision at this stage are critical. Any imperfection can doom an entire batch. These wafers are the blank slates on which the world's most advanced technology will be built. The journey from sand to silicon is a marvel of modern engineering. Now the real magic begins, building billions of transistors onto each wafer. Using photolithography, engineers coat the wafer with photoresist, shine ultraviolet light through a mask, and etch intricate patterns layer by layer. Each cycle adds new features: transistors, insulators, and microscopic copper wires. This process is repeated hundreds of times, creating a three-dimensional city of circuits just atoms thick. After months of painstaking work, the wafer is covered in a grid of identical rectangles, each a raw processor or die. Robotic needles test each die. Those that fail are marked for recycling. The survivors are ready for the next step, being cut out and packaged. Every working die is a tiny triumph of science and precision. Billions of transistors, all perfectly aligned, ready to power the digital world. This is where silicon truly becomes a brain. The raw dies, fresh from the wafer, are incredibly fragile. These tiny slivers of silicon, packed with billions of transistors, are susceptible to damage from even the slightest touch. They need a robust form of protection to survive the rigors of manufacturing, transportation, and ultimately, everyday use inside our devices. This is where the crucial packaging stage comes in. It's a highly automated and precise process, carried out in specialized facilities. The journey begins with each individual die being carefully cut from the larger silicon wafer using precision saws or lasers. This process, known as dicing, separates the individual processors, preparing them for their protective encapsulation. Each die is then meticulously picked up and mounted onto a substrate. This substrate is a tiny, multi-layered circuit board, often made of fiberglass or ceramic, that acts as an intermediary, connecting the delicate silicon die to the outside world and providing pathways for electrical signals. To establish electrical connections, incredibly fine wires, often made of gold or copper, are bonded to the die and the substrate. This process, called wire bonding, creates a network of microscopic connections, allowing data and power to flow to and from the processor. Alternatively, more advanced techniques like flip chip methods are employed. Flip chip technology uses tiny solder bumps to directly connect the die to the substrate, offering improved performance and density by linking the die to the substrate with microscopic precision. To manage the heat generated by the processor, a metal heat spreader, typically made of copper or aluminum, is added to the top of the die. This heat spreader not only protects the delicate die from physical damage, but also plays a crucial role in dissipating heat away from the processor, preventing overheating and ensuring stable operation. The specific type of package used, such as LGA or land grid array, commonly found in desktop computers, or BGA, ball grid array, often used in laptops and smartphones, ultimately depends on the specific requirements and constraints of the device in which the processor will be used. Packaging isn't just about providing physical protection to the silicon die. It's also about ensuring the CPU can effectively communicate with other components in the system and efficiently manage its thermal output to stay cool under demanding workloads. Selecting the right package is paramount to making a CPU reliable, efficient in its power consumption, and ready for seamless integration into real-world applications. Every single detail, from the intricate network of wire bonds to the carefully designed heat spreader, is meticulously engineered to maximize both performance and long-term durability. Only after the packaging process is complete and verified can the CPU proceed to its final series of rigorous tests. ensuring it meets the required quality and performance standards. The intricate journey from a fragile, exposed die to a robust, fully packaged processor is now nearly complete, marking a significant step in bringing cutting-edge technology to our fingertips. Before a CPU reaches your device, it must survive a gauntlet of tests. Each chip is powered up and pushed to its limits in specialized rigs, checking for flaws in billions of transistors. This is where binning happens. Chips are sorted by performance, power use, and thermal output. The best performers become high-end models. Others are sold as mid-range or entry-level CPUs. Even chips from the same wafer can end up in different product lines. Power and heat are especially critical for mobile CPUs. Only the most efficient make the cut. Every chip is laser-etched with its final specs after passing these tests. Those that fail are discarded or recycled. Only the best survive to be shipped to manufacturers. This final test ensures your CPU is fast, efficient, and reliable. The finished CPUs are shipped to manufacturers like Dell, HP, and Apple. At assembly plants, CPUs are installed onto motherboards, locked into sockets for desktops or soldered for laptops and phones. The rest of the system, RAM, storage screen, battery, is built around the CPU. Each device undergoes a full system test to ensure everything works together seamlessly. Only after passing this check is the device cleaned, boxed, and readied for shipping. The CPU, once just an idea, is now the beating heart of a new device. Every step, from design to assembly, is a blend of human ingenuity and robotic precision. The journey from silicon wafer to finished product is almost complete. Soon these devices will be in the hands of users around the world. Laptop and mobile CPUs may look similar, but their design philosophies are worlds apart. Laptop CPUs prioritize performance, drawing more power and using advanced cooling to handle demanding tasks. Mobile CPUs like Apple's A-series or Qualcomm's Snapdragon focus on efficiency, using just a few watts and relying on passive cooling. Mobile chips use big dot, little architecture, powerful cores for heavy tasks, efficient cores for background work. This hybrid approach, pioneered by ARM, maximizes battery life without sacrificing speed. Laptops are now adopting similar designs, blurring the line between mobile and desktop performance. Another difference: integration. Mobile CPUs are part of a system-on-a-chip, SoC, combining CPU, GPU, RAM, and more on a single chip. This makes phones smaller, faster, and more efficient. Laptop CPUs are usually standalone, with separate components for RAM and graphics. The result? Each device is optimized for its unique balance of power, efficiency, and size. After final tests, devices are packaged and shipped worldwide, a logistical feat spanning continents. When you unbox a new laptop or phone, you're holding the result of years of design, engineering, and global teamwork. Your CPU will power your digital life for years, running apps, storing memories, and connecting you to the world. But technology evolves quickly. New CPUs arrive, software demands more, and your device eventually slows down. Old devices become e-waste, a growing challenge for our planet. Responsible recycling recovers valuable materials and reduces environmental harm. The silicon and metals from old CPUs can be reused, closing the loop in tech's life cycle. The story of a CPU is one of creation, use, and renewal. Our responsibility is to ensure that story ends well for us and for the planet.